and he has three main themes to his research: neuroethology of navigation behavior in gastropods, lobster foraging behavior, and marine biofouling and anti-fouling. He is an invertebrate zoologist, an animal behaviorist, and a neurobiologist, and he's really interested in how the brains of marine invertebrates make them creep, crawl, and settle in response to food or mates or predators in their aquatic environment. So tonight he's going to be telling us about some of this fascinating research, exploring the navigation behavior of a variety of invertebrates in our waters. And so I welcome Russell to the Nova Scotia Institute of Science for our second last talk in our speaker series for the current year. So welcome, and thank you again for agreeing to present to us, and we really look forward to hearing your presentation.
Thank you very much, Tamara. I'm going to share my screen here first and get that working.
While you do that, I'll just, if you have questions as Russell's speaking, feel free to put them in the chat, and I can read them out on your behalf, or at the end of the talk, we'll open the floor to questions and you can turn on your microphone at that point and ask your question. Okay, over to you, Russell.
All right. First of all, I want to say thank you to the Institute for the invitation. It's a great honor. Really looking forward to this, and also to everyone who showed up on this April evening, where at least here it's not so pleasant outside, but of course we can escape that this year. So I'm going to talk about what I called for the talk title, Wayfinding Under the Waves, which is navigation behavior in aquatic organisms. And this is a behavior that this sea slug is performing before us right now, very slowly. But it's actually something done by all animals, at least all motile animals. So we're used to thinking about navigation behavior in the context of migrating geese, for example, moving long distances between breeding and overwintering habitats. But in fact, navigation behavior is simply any movement through a habitat to find or avoid a target. So whether it's these soccer players or wolves moving through the tundra, or indeed sea slugs crawling over the sea floor, it's all navigation behavior. And the targets are mates, prey, and what they're trying to avoid is predators. And so what I'm going to talk a bit about today is about how things work differently under the water than what you might have necessarily expected when you take an anthropocentric view. Humans navigate using vision and maps, and not all animals do that. And things work quite differently under the water, particularly with respect to vision. So I'll be talking about sea slugs, top right here. Snails on the right, this is going to be my work on the navigation behavior of these animals. And then I'm going to touch very briefly on salmon and turtles, which is work from other people that work on navigation and aquatic animals. And then I'm going to come back full circle to lobster at the very end, which is something I'm hoping to do in the future. Before I get into the fun of sea slug navigation, though, I do need to do just a little bit of hydrodynamics. This is really important underlying principle of how things work in water that has a really big influence on what the animals can and can't do. So chemotaxis is the navigation strategy many animals use to find odor sources. Odors are really important for navigation in the water. Anything that is in the water leaks odors, and those odors can be detected by animals, and they can either choose to move towards them or move away from them. In still water, those chemicals diffuse away from the source. So here's a high concentration of odors, and they diffuse out to a low concentration here in no flow. And in this case, the chemical gradient going from low to high can be used by an animal to find the odor source. And so that's called chemotaxis. And it works in no flow environments and also in what are called laminar flow environments. This is slow flow where there is little mixing. You can imagine a river is not laminar. There's lots of what's called turbulence and mixing that destroys these chemical gradients. So if you've got very slow flow, say in a swamp, then you can have these odor concentration gradients spreading still downstream, but still going low to high, and then from here, from high to even higher. And so animals can follow these concentration gradients back to the source in laminar flow. So this is called chemotaxis. And the thing to remember for the rest of the talk is this only works in no flow or very low flow, laminar flow environments. Once flow speeds pick up, things change. Turbulence, this mixing, increases as flow speeds increase. And this is a visualization with dye, which shows what happens when you've got a chemical dissolved in water that is flowing with turbulence. Those nice, smooth concentration gradients have been completely destroyed. And this means that animals cannot use them to find the odor source. Here's the odor source. You have this turbulent flow mixing the odor concentrations into these filaments with high and low concentrations, essentially randomly distributed. And in this case, animals do not use chemotaxis because it will not work. Instead, they use what's called odor-gated rheotaxis. They turn on rheotaxis with odors. So that's the odor gating of rheotaxis. So they're following the flow, that's what rheotaxis means, when they detect the odors. And this works because it's the flow that transports the odors away from the source. So the flow is moving downstream here. If the animal down here detects an odor, it can move upstream to find that source. And so in turbulent flow environments, animals do not use chemotaxis, they use odor-gated rheotaxis. So those are sort of two key principles to remember for the rest of the talk. Okay, so now I'm going to take you away from our coast over to the west coast, to the near shore habitat where you find these soft corals called sea pens. And we're going to do a bit of a swim through these so you can get a feel from them. They're about a quarter to half a meter high, a foot or so high. And these are colonial soft corals, among which you find living sea slugs. So here's one of these sea slugs. This is Tritonia exulans, and they live their lives in these sea pen beds. And they live here because they eat the sea pens. Their lives are really quite simple because they only have one prey item. They eat these sea pens. They only have one predator, sea stars. Nothing else eats them because they taste bad because they eat the sea pens, and the sea pens are chemically defended. And so the slugs are probably chemically defended also. Okay, so they've got one prey, one predator. They don't have to worry about sex in the sense of male versus female because they're all hermaphrodites. So whatever other slugs they meet, they can mate with. Sperm goes both ways. So this creates a very simple navigational system with very few targets, which means we can unpack it much more easily than many animals. In addition, these animals are blind. So they really are using just odors and flow for the bulk of their navigation behavior. So it's a great place to study this. Okay, so as I said, they eat sea pens. This is what it looks like. This is the fastest behavior these animals perform. And that is what's called a bite strike. You have to do it quickly because the sea pens are soft corals. They have only a small hard skeleton that runs the length of down here, and otherwise they can deflate and pull into the sediment like this. So the slugs essentially browse on, you can see the torn leaflet here. The slugs browse on these. That's the extent of their predatory behavior. That's all they eat, and that's how they do it. As I said, they mate with Tritonia. They're hermaphrodites, so they will find each other and then align head to tail and stay here for, on average, about 3 hours, okay, mating. But again, no complications with finding the wrong sex. They can mate with any other slug. And then they worry about sea stars because the sea stars would eat them if they could, but the slugs have this extraordinary escape swim behavior that they use to get away. And they don't like to use this because it's costly. It's energetically costly, but it also gets them up off the seafloor and gets them away from the sea star, but it could also end up with the tidal currents sweeping them away from their sea pen food. So they try to avoid this circumstance by crawling away from the sea stars. You can see a second slug here going through a bite strike in the background. Okay, so I've just told you some stories about how these guys navigate. Here's some evidence, at least in the form of some more details videos of it occurring. I've done extensive hundreds of hours of video analysis to support this, but I'm not going to bore with you with the statistics tonight. This is an example of navigation behavior to find food. So we've got a slug here. The camera is now about 1.5 meters above the seafloor. We're looking down on 4 sea pens here, and then there's a slug that you're not going to be able to see until it's crawling. And it's going to take a strike at this one, and it's going to crawl off the screen and then come back this way. And there's a dye releasing system over here, which is going to allow you to see the flow. And what you want to notice is that when it's crawling towards the sea pen, it's crawling upstream. And again, when it's crawling towards these sea pens, it's crawling upstream. Here's our slug crawling. There's our sea pen, and it gets struck, and it pulls into the ground, the substrate. Falls off screen. Here's the shift in flow, and it now is downstream of these. Falls and creates a strike. So you watch enough videos and you see this happen again and again and again. The animals consistently approach from downstream, and it starts to make you think, well, they're probably using odor-gated rheotaxis to find their prey. And indeed, the environment is turbulent. Chemotaxis would not work here. We can see the same thing with mating. This is a rather complicated video because the flow changes so much. We've got 2 slugs here, and they are eventually going to be able to mate. For a while, the number 1 slug is downstream of number 2 slug, and so it heads for it. But then there's a change in flow direction, and it gets led astray. And then eventually 2 ends up downstream of 1, and they end up mating over here. The video is going to change to a motion-enhanced view that allows you to see the slugs and the dye plumes more clearly. So here's slug 1 crawling towards slug 2. Here's the switch to motion enhancement. So slugs that are moving, we can't see slug 2 because it's not moving. Here's our dye plume. This guy's crawling upstream, but then the flow changes, moves off here, and finally gives up. Rather disappointed. The flow keeps changing, and now you can see slug 2 is downstream of slug 1. It wakes up, does a U-turn, and starts following. Gets a little off track here because of a sea pen, but sex is more important than food. And so they do a little bit of a rotating dance here, and then they get to do their 3-hour mating. So again, highly suspicious. Looks like odor-gated rheotaxis. Okay. Now we moved our camera closer to the sea floor. We've got a slug right here, and then 3 sea pens just for ambience. I'm going to deliberately place a predator in here, and you're going to see